Welcome everyone. Today I'm examining the two script files that we saw during lecture 3. And in particular, if you remember, in lecture 3, we focused on the problem of the recursive estimation of parametric models by considering different structures and input signals. If you remember again, the properties of the input signals, in particular, the properties of persistent excitation represents an important point that determines the accuracy of your model. So let's see the two examples that are presented here, and in particular the two files, the script file lecture 3 exercise 1, and let's download it, and save destination X as lecture 3 exercise 2, and then we will see them in detail. So let's open the MATLAB and let's examine the two. In particular, let's start with the second one and exercise 2. So I briefly comment. So exercise 2 in particular, we are using a number. So then also the symbols are consistent with the symbols, the mathematical symbols used in the equations of the lecture. So in particular for this example, we consider a number of samples 5,000 and a sampling time of 1 second. Is not in general, but it's okay. And then we are generating these represent the equation error that is modeled as a Gaussian noise with a standard deviation of 0.1 and a zero mean value. In particular, we are in this line we are removing the mean value of the sequence. So we are sure that with this operation we have a signal which has zero mean and 1 as a standard deviation, and then we multiply with the standard deviation we want, which is 0.1. And then let's determine the inputs for our model. In particular, we are considering a pseudo-random binary sequence. So if you remember, it represents the best input for identification, and we are considering in this example half of the in the middle, so during the half of the sequence in the middle, we have the case of the change of our parameter. So we are trying to see the performance of our models when a change in the parameter, so the model is changing. Not really its structure, because the structure is fixed, so it means that if I'm considering an ARMAX model, as it's described here at the beginning, is the same during the sequence. But you can see here that before the change, we have the parameters A1, which represent the parameter of the autoregressive part of the model, and is 0.8. And the deterministic part of the model is 0.5. And after the change, we have that the autoregressive part, the parameter of the autoregressive part becomes 0.2, and the deterministic part is described by parameter 0.1. So we have the theta, which is theta 1, star. So star means that is the real value. So real, of course, is the parameters that are generated. Ideally, the ideal model, and d is the length of the parameters of the parameter vector that you need to estimate. So we call G1 and H1 the deterministic and the stochastic part, respectively, of your ARMAX transfer function, and the same for the model after the change. And then we are simulating the output of the first and the second model, and then we aggregate them in order to have the output, the overall output that it seems that it is generated using two models. And then as a starting point of our recursive algorithm, if you remember, P0 represents the covariance matrix of your parameters, and in this case is represented by a quite high value, because the initial estimation of your parameters is 0, so you don't know the initial value, and we are considering a lambda, different values of lambda, which is your forgetting factor. And let's try it with the value of, for example, 0.98. So we are using the function recursive ARMAX, and you can see here that you have the output, the input. So you feed this function with the number, with the vector of the output. The input in this case is a scalar, and you have the delays of your models, of your parameters. So it's 1, 1, and 1. Then you have a forgetting factor, and with value lambda, theta 0, and p0. Your model, your ARMAX model, is obtained as a single model. So the function ARMAX estimates the parameters as if the overall sequence were generated by a single model. And with this function, you have also an estimation of the numerator and the denominator of your transfer function, and also the accuracies of these parameters. And then I will plot the values of the parameters before and after the change. So I will compare the results of the estimation, as you can see here. So I'm estimating the plots of. So I'm depicting the plot of the theta estimated as a recursive model, in particular as A, and then the B parameter in two subplots, and a comparison of the model that the comparison of the model is here as a recursive and the parameter of the model. And then the same, so I'm comparing the tracked parameters and the estimated parameters using the least square, and the same for the parameter B. So let's see what happens if I run this example. This example can be used for comparing the performances of your estimator when, for example, different values of lambda are used. So let's try to run the first this example. Okay, there is a warning, but it's not a problem. So you can see here that you have two pictures, and in fact you have the tracking of your model. So you have the two. The comparison, as you can see here, that we are comparing the true and the tracked parameter here, and in the second picture you can see here perhaps the color is not so bright, but you can see here that the classical, let's say the least square, is trained to, well, B is clear because it seems that the value provided by the least square, the normal least square, is something in the middle between the two parameters. So the non-recursive model seems to understand that the data are not generated by the first or the second, but is something in which is in the middle. Well, of course, for the case of the first parameter, this fact is not so clear as for the case of B, but you can see that the estimated parameter is something in the middle. So let's try to see what happens if, for example, we modify the value of the lambda of the forgetting factor, and for example, let's try to put a value of 1. So let's see what's happened. What means when lambda is 1? If you should have understood that what it is the case of the value of lambda, and we will see it from the simulations. In fact, you can see here from the second picture that if you see that the tracking, the recursive least square, the solution tends to the classical least square. So it's something that we saw in the algorithm, because in fact lambda equal 1 means that the recursively square algorithm tends to the classical least square. Let's see what happens, for example, if we use a lower value. So the 0.98 can be used as a reference value, because it's something, if you remember, a general recommendation is that the value of the forgetting factor should be taken in between 0.97, 0.99, so it's not too high, but not also too low. And let's try to use, for example, 0.97 that can represent the minimum of the value that you can, and you can see here that you can start to see here that in fact the accuracy of your estimation is deteriorating, because you see that is the accuracy in, so it means that the mean value is very noisy, so it means also that in fact as soon as the more you reduce the value of the lambda factor, the more you increase the filtering, so the bandwidth of your filter is increasing. So it means that you are amplify the noise affecting the data. And this is even clearer if you, for example, you use a lower number for, of course, is very small, but 0.7 represent an invisible number, because in fact, as you can see here, 0.7 is very clear from, for example, the second parameter is also the value of A of the estimation. Of course, the tracking is very quick, and it can be seen here, but the accuracy is very poor. And again, if you even you choose a lower number, 0.5, which is really too small, and something can happen because you can see here, for example, for the case of the parameter A, everything is not clear, so you cannot understand that there was a change in the parameter. So you should select carefully your parameter, the forgetting factor, because if you remember from your algorithm, it represents the number of samples that are that the algorithm forgets during your filtering. So, depending, for example, on a preliminary knowledge of the samples, you need to consider movie samples that you need to consider, so you can derive the optimal value for your lambda. But it's not really an issue to find this parameter, because normally you select the number 0.7, 0.8, and it's very good. So this is not represent a real problem. So if the example is clear, we can close and move to the first example. So let's try to close this one. And then, so another remark, so don't care about the warning, because it's a problem that the functions we're using are slightly different with the new releases of MATLAB, but it's not a real error, just a warning that in the future releases these functions will be modified and some of them will be removed. So let's check the second, which is the first one, and the first one is it represents, so we are considering a number of 1,000 samples, and again we are considering the presence of an equation error, and then we can select. We can select two signals in order to compare the persistence excitation properties of our input. So we have the case of the pulse signal, which, if you remember, has a very extremely poor excitation property. So it means that it's persistently excited of order 0. A square wave, which has a very quite better, slightly better persistent excitation feature or properties, but is not really equal to the pseudo-random binary sequence, which represent the best solution when you want to identify a model. And then this is the comparison when, for example, the model is estimated with the assumption that you are using the same class of models that are have generated your data. So in this case, let's start, for example, with the case that you are we are using a ARMAX model for generating your data. So if ARMAX model, we are generating effectively our data with a ARMAX model, and we are assuming we are generating the simulation of the output given depending on the input. So we can, for example, now assume that we have a pseudo-random binary sequence, so which is represent the best for your identification, and then we assume, again, as in the previous case, the two solutions when we have the recursive least square and a comparison with the two parameters estimated and the solution of the given by the least square, classical least square, and also here we are considering, for example, the values with the accuracy. So let's try with these assumptions and let's see what happens when we launch this, we run this figure. So you can see here that from feature 1, you can see here that the, well, in fact, the recursive estimation tends to the real value, to the value of the parameters, and after an initial transient, it goes quite near to the value. And we can see here from the figure 2, there is also the comparison that it seems that you can see here that the estimated, I don't remember which value of forgetting factor we assumed, but I think that lambda, okay, lambda is 1, so we obtain the same value of the classical least square. Okay, so we can put here 0.98, which can represent a good value, and that will let's see what happens. So we can see here that the estimated value is varying around the true value, and also we have the the picture 3 is representing the accuracy of your parameters, and you can see here that the tracking is quite it's not very accurate. This depends on if you see here. I don't know if you have noticed, but we are considering a value of the noise quite important, because in fact if we reduce it, so we have a very small noise, so it means that the signal to noise ratio is quite high. This improves the results as we see here, and in fact you can see here that with a very low noise, with a very small noise, the accuracy of your tracking algorithm tends to the accuracy of your the real value tends to the real value of your model. And because I recall you that we are assuming that that also is so the noise in this case is very small, and we have a pseudo-random binary sequence, and the model, the assumed model is the same of the model, the system that generated the data. So everything is good. So let's try to remain with this this assumption that the model is the same that of the system which has generated the data, and let's try to change the let's try to slightly change the level of the noise to see that, of course, the performances are deteriorating, but not so they are not so critical. So you can see here that the results, so the estimation is quite good. And let's try to, as a second example, let's try to consider, for example, again, we are assuming that we are considering a RX model, so everything is fine for the assumptions of ideality. And let's try to see instead to deteriorate the input signal. So we are using the pulse signals, and you see here that the pulse is you have a pulse at during the 1/3 of your sequence. So, and let's check. The result. So at the beginning, this means that at the beginning, your model is not providing any interesting result, because you can see here that you see that you don't have any estimation, any effective estimation, especially for the parameter B, because you are missing the deterministic input. So you are only estimating something that is quite close to the A value, but the B, because the persistent excitation conditions are missing during the first third of your estimation. So the estimation is quite accurate only for the second series of data. And you say here that, of course, there is a bias in the estimation of your parameters. And let's see if what happens if instead we are considering a square wave, which is not really the best, but can be considered in something that can be useful for the identification. And then let's see what happens. And in fact, you can see here that the properties of your estimation are better. Even if you can see here that for the A the accuracy is improved, but for the case of the parameter B is highly relying on the lack of persistent excitation. So you have an effective excitation only during the abrupt change of your wave, and then you lose, and again you are tracking the parameter, and then you lose it, and every time you have like a disturbance in your estimation. And let's see what happens if, for example, again we are considering a pseudo-random binary sequence, but let's see if the model is not the one that if the assumed model. So we are assuming that we are using an ARMAX model for estimating here the data, but the data are generated by an ARMAX system. So let's see what happens. Of course, you can imagine that the estimation is not consistent, because the model is not the same of the system that has generated the data. So let's see what happens. And in fact, you can see here that at least from there is something that is not very from the figure 1. So it's something that, well, the recursively square is tracking your parameter, but with an ARMAX model, let's see the second function, the second plot. Let's try again to have the second. Here, the second plot, in fact, the estimation provided by the recursive least square is quite different from the one of the real data. And this is even more serious if, for example, we are assuming again an ARMAX model, but for example, now we are using a pulse signal. So you can see here that in the pulse signal, you can see here that the your estimation is effective only after the pulse, as in the previous case, but the estimation is quite far from the real one, and it improves if we are considering a square wave. You can see here that that is one. Let's see, check the second one, and again, in fact, you can see here that the estimation provided by the least square is quite different from the one provided by the recursive and the least square from the real one. And let's see what happens if, for example, for the square wave has a period of 100, and if we consider again a number of, for example, a number of 100 samples, 1000 samples, and a sigma which is quite high, 0.3, which is the level of noise is quite high. And you see here from the second one that the accuracy of the estimation is modified, and it was reduced with respect to the previous case, because of course the level of the noise, even if the parameter or the model is the same of the system that has generated the data, is the same, so the estimation is deteriorated. So this was an example of how the quality of the inputs, the inputs that are used for the identification, determines the quality of the estimation, and also the fact that the model of the data, of the model that has generated the data, the system that has generated the data, is the same assumed for the estimation. It represents a real point for the identification. So, okay, I think that this should help at least to understand some features of when we consider the recursive estimation here in the lecture 3. Okay, thank you for your attention.